that the Arctic sea ice is at an all-time low. It has already broken the all-time record, which was set in 2007, and there's still a couple of weeks to go before the normal minimum occurs in Arctic sea ice. And so the whole ecosystem that the polar bear thrives in is in jeopardy. So the polar bear is indeed one of the poster childs. Let's see if this works. I like to start a talk like this by pointing out the fact that the atmosphere is at global commons. There are two main global commons that we refer to. The other one is the oceans. They're shared by all. And a few years ago, there was these attempts by people to fly a balloon around the world. Ooh, can we turn this one off, maybe? And maybe that'll cut down on that. And don't make it too dark. I don't want people to go to sleep. It took a couple of weeks to go all the way around the world. You could track that. And so one of the key points is, as meteorologists have known for a long time, that the air over China one day is over the United States 5 days later. 5 days later, or something like that, it's over Europe. And so if we put stuff into the atmosphere, as we do, or if the Chinese put stuff into the atmosphere, it gets shared among all of us. All right. We use the atmosphere as a dumping ground for all kinds of stuff. Every time we breathe, of course, there's carbon dioxide that goes into the atmosphere, but we do a lot more than that through the burning of fossil fuels. And some of this stuff lasts a long time, and it's shared with all. Carbon dioxide is one of those things. There is some stuff, pollution, visible pollution, that we put into the atmosphere that gets washed out fairly quickly on a time scale of about a week. If you wash your car and a little shower goes by, after the shower's gone by, there's all these spots on your car. And rain, in fact, is very effective at cleaning the atmosphere of those kind of pollutants, but not the gases, the carbon dioxide. So we'll look at that in just a minute. So to summarize this problem overall, firstly, there are some symptoms. The planet's temperature is increasing, and carbon dioxide is also increasing. So we can observe this, and I'll show you some of the facts behind that. The diagnosis is that the human activities are causal because we produce the carbon dioxide, and the carbon dioxide is related to the fact that the temperature is increasing. The prognosis, the outlook, is for more warming at rates that can be disruptive and could cause strife. We've seen some really good examples of that this summer in the United States. And the treatment for all of this, two key words that are used: mitigation, which is to reduce the emissions, cut down on the problem that continues to develop, and secondly, adaptation, which is really planning for the consequences, or else we live with the consequences. So we'll talk about those kind of things a little bit later. So firstly, where does this stuff come from? You're well familiar with this. This is the burning of fossil fuels in different shapes and form. Carbon dioxide goes into the atmosphere. Where does it come from? This is the time series from 1800 estimates of the main sources of our energy. And if we highlight the fossil fuel contribution, you can see that it's by far the dominant contribution. And notice the shape of this curve. It's a fairly exponential curve, and so most of this stuff has happened actually after about 1960. Everything that happened before then is relatively unimportant compared with what we're doing today. And down here at the bottom, we've got the renewables and the biomass. This is the carbon dioxide record, which was set up by Dave Keeling in Mauna Loa. I knew Dave quite well. In 1958. And firstly, it has a sawtooth character to it, which is the annual cycle. This relates to the greening of the northern hemisphere in the spring and the summertime. Through photosynthesis, the plants take carbon dioxide out of the atmosphere, and there's a drawdown of carbon carbon dioxide in the atmosphere. In the fall and in the winter, the leaves on the forest floor decay, put carbon dioxide back into the atmosphere, and that's this annual cycle that you see here, this sawtooth character to this thing. But in addition to that, you'll see that there's an increase going on. And if you look carefully, you will see also that the rate is increasing. This is ominous in itself, because some of you may be aware of the Kyoto Protocol that was designed to turn this around in the other direction and start to reduce the rate of increase of carbon dioxide. This highlights the fact that carbon dioxide has a long lifetime in the atmosphere, over 100 years. Some of it lasts for a very long time before it gets taken out. And the main natural process is, of all these stuff that gets burned, about half of it disappears, and about half of that goes into the biosphere, so it's producing more leaves and plants and twigs and things. About half of it goes into the ocean, and it's causing acidification of the ocean. And in the ocean, it gets taken up by little organisms. It goes into the shells of organisms. They fall to the seafloor, and they basically get taken out of the system. It forms limestone, stuff like that. It also gets taken out of the system through the weathering of rocks. But that's a very slow process. A lot of it gets recycled. We can talk a bit more about that later on. So where does this stuff actually come from? The most important thing overall is actually the accumulated emissions because of the long lifetime of carbon dioxide. And the US is responsible for more than anyone else, around 27% through 2010. The rest of Europe is down here. We've got Germany and the UK down here with 12%. So together with this, Europe is somewhat more than the US. A bit disconcerting, isn't it? Ringing in the background. And you can see the contributions from other here. Accumulated, China is estimated about 10%, and you can see ships and aircraft 2%. Now we can contrast this accumulated amount with the 2010 emissions when we break it up. And you'll see that China constitutes about 24% of the total emissions. The US is about 17%. So relative to the accumulated value, the current rate that people are putting stuff into the atmosphere is much greater comparatively in China and also in India. It's doubled. Europe is, Germany, the UK down to 2%, and the rest of Europe is 9%. So Europe as a whole is around 13% less than the US. And so Europe has reduced their carbon emissions compared to the US. That also tells us a number of things. It tells us actually we could do a whole lot more, and Europe has been a leader in things like the Kyoto Protocol. It also tells us that these growing nations are now a substantial contributor to this problem. One of the arguments that is used in the international fora about carbon dioxide and the fact that it might be a problem is to say, yes, but it's not the total emissions that matter, it's the emissions per capita. This is the argument that China uses. Of course, they've got a lot of people. And so this is a little dated now. This is 2007. The per capita emissions are given here. And so China is about a factor of 4 less than the US in 2007. Might be a little higher than, China might be a little higher than that now. India is a factor of 10 less. The EU, the European Union, this is quite interesting, is a factor of about 2.5 less per capita than the US. Now this is interesting when you think about it. The standard of living is very similar in Europe. So why is this a factor of 2.5 less in terms of the total emissions? Yeah, have a guess?
Yeah. My name is Mary Riley, and I'm going to attribute it to the fact that the United States grew up during the Industrial Revolution. So our infrastructure is based on cheap, abundant fossil fuel. The way our houses are built, the way our roads are constructed, the way the size of our automobiles are all contributing factors to these numbers. As compared to Europe, that just doesn't have that much to waste.
Well, I think there's some simpler answers to that. I mean, some of you have traveled in Europe, I'm sure, and
smaller cars.
Tax policy.
Price of gas.
The price of gas. How much, if you've ever driven in Europe and you buy gasoline, it costs what, 2.5 times more than it does here, right? And people drive smaller cars.
More efficient.
The cost of electricity is also higher because it has a carbon tax built into it. It wasn't put in there as a carbon tax. It was done to ensure that efficiency occurs. And so it has this effect that people use these precious resources differently than we do in the United States. But this also tells us, I think, that we could probably reduce our emissions by a factor of 2.5, probably with very little impact on our standards of living if we went about it in the right way. So part of this problem is of course, it's not a problem from the standpoint of the climate system as a per capita problem. It's the total amount that matters. And so, therefore, if you argue on a per capita basis, as China does, to say, but we have a lot less emissions than the U.S., and therefore we can continue to emit more and more and more until we're at the same level as the U.S., then the planet is seriously in trouble. And so part of the problem is population. Indeed, now China has controlled their population, but, you've all heard, I'm sure, that we've just gone through the 7th billion of the number of people on the planet, and this is the time it took to generate 1 billion people. 2 billion took 103 years after the first billion, and, now it's been, an extra billion is occurring about every 12 years. It's projected that we could be over 9 billion by 2050. And so the current rate that we're adding people to this planet is about 1 million people, a city of 1 million people every week. Isn't that incredible? How are we going to feed and water all of these people? This is a big issue, and it's not talked about. All right, turning now to the climate problem itself. There is a natural greenhouse effect. It's why this planet is habitable. And the most important greenhouse gases are water vapor, carbon dioxide, about a quarter, ozone, methane, nitrous oxide make up most of the rest. Most of the atmosphere is made up of oxygen and nitrogen, O2, N2, two atoms per molecule. Those are not greenhouse gases. As a rule of thumb, any molecule that has more than 2 atoms per molecule is a greenhouse gas. So water vapor, H2O, has 3. Carbon dioxide, CO2, has 3. And it relates to how that molecule and the different atoms can actually jiggle around one another and therefore relate to how energetic they are and whether they can absorb energy and then re-emit it. And so that's sort of a rule. You know immediately whether a substance is a greenhouse gas or not. Water vapor, however, has a lifetime of only about 9 days in the atmosphere on average, whereas carbon dioxide has a very long lifetime. So does methane. Methane's about 10 years. Nitrous oxide is over 100 years. And so these are increasing in the atmosphere. Ozone, most of the ozone is in the stratosphere. There's some tropospheric ozone that has a lifetime of about 3 months or something like that. It's associated with cars and the photochemical processes. So the overall schematic of what happens is that the sun is shining down. Some of it's reflected from clouds, some of it's reflected from the surface. Most of it's absorbed at the surface. And then to have an equilibrium climate, the Earth has to radiate back to space. But with the greenhouse gases and with clouds in the atmosphere, some of that radiation is trapped and therefore it can't escape directly to space, and then it gets re-radiated at the temperatures of the atmosphere, which is much colder above the surface, and therefore this provides a sort of a blanketing effect for the climate system, and the greenhouse gases produce a warming effect. And so it's much warmer on the planet because of these greenhouse gases than it would be without them. And it actually makes the whole planet habitable. To give some idea as to how much energy is actually flowing through the climate system, I put some numbers up here. The incoming energy from the sun is equivalent to 175 petawatts. That's 175 with 15 zeros after. This is the amount which is intercepted by the cross-section of the Earth of the solar radiation. So it's a huge amount of energy. About 30% gets reflected. And so about 122 petawatts is absorbed. In other words, that's the amount which powers all of the weather, all of the hydrological cycle. Very important. But the biggest power plants we have in existence are of order 1,000 megawatts. And that sounds like a lot. You know, some of them are getting up to 2,000 megawatts. And more commonly on a day-to-day basis, we think in terms of a 1 bar heater, which would be a 1 kilowatt. That's about the same energy that's put out by an iron. The audience here actually knows what an iron is. If I talk to the youth these days, they don't even know what an iron is. And you're familiar, of course, with a 100-watt light bulb. In fact, with a crowd in the room like this, all of you are radiating at about 100 watts. That's about the energy that you're giving off right now. That's equivalent to about a 2,000 kilocalorie diet per day. Anyway, we might come back to that. The energy from the sun then is 122 million of these huge power plants. And if we add up all the power plants around the world, and if we also add up all of the other coal and wood that is burned, that doesn't go into energy or anything like that, it turns out the total number is 1/9,000th of this number, 1/9,000th. So it can be very important. It is very important in cities. And so in a big place like built up like Manhattan in New York City, there is a distinctly different climate because of all of the human activities and the human space heating and the use of energy. So it's called an urban heat island effect. These are related to the built-up areas of cities, but still they're relatively small compared to the flow of energy through from the sun. It's still about more like a 10% effect, but on a global basis, it's about 1/9,000th. And so it says that the direct human influences are relatively tiny versus nature. And the main way humans can actually affect the climate system is by altering these natural flows of energy through the climate system, by blocking the energy that's escaping to space by changing the composition of the atmosphere. It's often argued that the sun is the cause of all of everything that's going on. It's got nothing to do with humans. Well, this is the record we've got from the sun. The satellites in space have been measuring it since 1979, and we've got some indications clearly before then as to what had happened from other observations. This is the record, and so there's a sunspot cycle, which is an 11-year cycle that you can see here. The most recent downturn is the lowest on record. If anything, there's a slight cooling from the effects of the sun. This total range in here corresponds to around 0.2 watts per square meter out of 240 watts per square meter. This is per square meter in terms of the overall flow of energy through the system. So it's about 1/1000th of the total flow of energy through the system. It's very small. Because this rebounds, it has had very little effect on climate overall. But the sun goes through these active phases and quiet phases. So In the IPCC, we do an assessment of all of the evidence of climate change, and this is a summary here. I'm going to go through some of the evidence here in terms of the temperatures, sea level, things related to storms, drought, heat waves. I mentioned the ocean becoming more acid, and then on the cold side, the decreases in glaciers and sea ice and so on. So let's have a look at some of the evidence. In terms of the oceans, there was a very nice turn of phrase, I thought, by Nicholas Gruber, who said the seas are warming up, turning sour, and losing breath. And so they're not only warming up, they're also becoming more acidic, and they're also losing oxygen because of nutrients from land and the effects of the warming, which produces increased stratification in the ocean and cuts down on the mixing. And so there are more dead zones developing in parts of the ocean. And so there are effects that are not simply related to climate change, that are also occurring in the ocean. This is the global mean temperature record. This is the one that's put together by NOAA. The 0 on here corresponds to the average for the 20th century. So by definition, the 20th century averages out to 0. And then this is the annual carbon dioxide values. Here I've taken out the sawtooth character, and I've extended it back in time using the values from bubbles of air that have been extracted from ice cores in Greenland and Antarctica. And so we have very good knowledge of how carbon dioxide has changed over time. And I've put them together like this with the scale on carbon dioxide over here and temperature on the left to suggest that there's a relationship between these. Because in my lab in Boulder, we think we can prove that that's the case. And I'll show you some examples of that later on. But you'll see there's also quite a bit of ups and downs. And so this is the natural variability. And the peak values in here tend to be El Nino events, if you know what that is. We're going into an El Nino at the moment. The other key aspect beyond temperature is the fact that the very important role of water and the effects on storms. How do we control heat? I mentioned that you're radiating or giving off about 100 watts each. And the main way we tend to do that is actually through perspiration and evaporation of moisture, and that's what keeps the body cool. There's also a certain amount that actually is coming out in the form of radiation. We prevent that, though, mostly by wearing clothes. Now, out in the West, we have evaporative coolers. We call them smart coolers, and we can keep the homes cooler through evaporative cooling at the expense of moistening the atmosphere. This doesn't work in a humid environment, but it does work for the planet Earth. Evaporation keeps the planet cool because the heat goes into evaporating moisture. And that's what actually drives the hydrological cycle. That's what produces rain. It produces all of the storms. And so a lot of heat goes into that rather than raising temperature. You know, another example, if it's been raining and the sun comes out, the first thing that happens is that the puddles dry up, and then the temperature increases, and the heat can go into increasing the temperature. But otherwise, a lot of it goes into drying. Now, this is a summary of the effects related to water, and I'll show you some of these and some of the consequences of them. Firstly, we have warming, global warming. There's more heat. That really means global heating, and so there are higher temperatures, and we've just shown you some of that. But in addition, with higher temperatures, the atmosphere can hold more water vapor. And the number is about 4% per degree Fahrenheit. And this is about what is observed, so that with a 1 degree Fahrenheit increase in temperature since the 1970s, going along with that, over the oceans, there's a 4% increase in the moisture in the atmosphere. 4% more moisture in the atmosphere over the oceans. Where there's plenty of moisture, actually that number applies. In deserts, it doesn't matter how warm it gets, there's no more increase in moisture. The moisture's got to come from somewhere. And on land in general, the number is about 2 to 3%. So the atmosphere is moister than it used to be. Didn't I say that one of the greenhouse gases was water vapor? I did.
Yes.
That means there's a positive feedback. So as we warm the climate, more water vapor produces extra warming. Now, in addition, if there's more heat, some of that goes into evaporation. It produces the extra water vapor in the atmosphere, and it can give rise to extra precipitation. And so, in places where it's not raining, things dry out a little quicker. We've seen a very good example, or good examples of this across the United States this year. The drought sets in a little quicker. It's more intense. It's longer lasting. We saw good examples of this in Texas last year. Somehow the governor of Texas doesn't seem to believe this. More intense rains and snows is one of the consequences of this, and more intense storms. And so we end up, as a result of all of this, with both more floods and more droughts in different places at different times, or even in different places at the same time, or at the same place at different times. But this is one of the consequences, more extremes on both ends of the hydrological cycle. So the basic idea here is that you have storms. This is more like a thunderstorm, but it only rains over about 7% of the globe at any time, 7%. And it rains very hard. The average evaporation rate is very small. It's only a quarter of an inch per day or something like that. So how can you get more than a quarter inch of rain? The reason is these storms reach out with their winds, with their circulation, gather in the available moisture in the environment, bring it into the storm, concentrate it, and dump it down in the form of rainfall. And as a rule of thumb, 7% of the globe is about 1/16. Take the square root of that, 1/4, a factor of 4. On average, weather systems reach out and grab the available moisture from about 4 times 16 times the area, 4 times the linear dimension of the rain that's being produced. And so a big storm in the Ohio River Valley, where it's raining over, say, a 500-mile radius, huge storm, is reaching out to the Gulf of Mexico and the tropical Atlantic to get its moisture and bringing it into that storm. As a result, if there's more moisture in the environment, it rains harder. And we have very good evidence in the United States that it rains harder than it used to. At the top level, there's been something like a 20% increase in the heaviest rainfalls that occur. And this increases the risk of flooding. And we've just seen an example of this right down with Isaac in the New Orleans area, and now extending further north. The amount of rains that we're getting now are simply much greater than we would have gotten under the same circumstances 30 years ago. So another factor is that more precipitation falls as rain rather than snow, especially at the beginning and the end of the season. And so the winter snow season is shorter. In addition, snow melt occurs a little faster and sooner in the spring. This leads to earlier runoff and peak stream flow. In the Sierra Nevadas, the peak stream flow occurs about 7 to 10 days earlier now than it did in the 1970s. The snowpack is therefore less when you get into the middle and late spring, and the soil moisture is less as the summer arrives. This increases the risk of drought. It increases the risk of wildfire. And this is an example of the 2002 Hayman wildfire in Denver that ended up burning some 400 structures. How is precipitation changing as a whole around the world? Rather than show you changes in precipitation, what I've done here is to show you changes in the river drainage basins. Some of you may recognize part of the Mississippi here, but it's combined with other river basins here. And this is the trend from 1948 to 2004. I wish we had better data, and I wish we could bring this more up to date. This looks a bit like a checkerboard, but let me show you some patterns here. In general, east of the Rockies, it's been wetter in the United States and North America. It's been wetter generally through northern Europe and Asia, and it's been wetter in Argentina in particular. And generally, through the tropics, it's been drier. It's been especially drier in Africa, extending up into the Mediterranean. And this also extends right up into the southwestern parts of the United States. So there's a pattern to this. What about storms? This is actually a picture in 2005 of Katrina. You know, 2005 was a fascinating season. It had 4 Category 5 storms, broke all kinds of records. So if we look at those records over time, what I'm showing you here since 1944 are in red the number of Category 4 and 5 storms, in gray the number of hurricanes, and in gold the number of named storms, storms that were given a name, the tropical storms. And also I put a curve through these to indicate some overall trends. And you can see the last couple of years have been added on by hand at the end here. 2005 stands out, holding all of the records. Now down below in the tropical Atlantic region where most of these storms form, I'm also showing the sea surface temperature record. And in general, high values in this correspond to peaks in the tropical storm activity. So 2005 was the warmest on record in that particular region. There are some years, however, so here's a year when there was a lot of activity. Here's one where there wasn't. And what happened in 1957 is that there was an El Nino that went on. When there's an El Nino, all of the action goes out into the Pacific, and the activity in the Atlantic is suppressed. And it turns out the most active year on a global basis remains 1997. 1997 turns out to be this guy here, where it was actually not very much activity in the Atlantic, but there was some more activity everywhere else around the world in that particular year. And so the activity was suppressed in the Atlantic as a result. 1997, you may remember, is when the word El Nino actually came into the American vernacular. 1997-98 was the great big El